Okay, here's our next section, limits at infinity. Gonna start off with a definition. It's kind of like an epsilon delta definition that we saw before for our normal limits. Limit of f of x as x approaches infinity equals L means if for all epsilon greater than 0, there's an m large enough greater than 0 such that if x is bigger than m, then we have this condition. This condition graphically looks like this up here. You have f of x reaching L in this band, L minus epsilon, L plus epsilon. And after you get past a certain point, a certain value of x, m that is, then notice the graph is trapped between L plus epsilon and L minus epsilon. So we can make that as tight as we want. If we get if we make m greater and greater, we can shrink that. And epsilon can be shrunken down. As long as we make m big enough, we can make this happen for any epsilon chosen. We can get this curve to be trapped inside here. That's essentially what it's saying. And the same thing happens for negative infinity if you're going in that direction. So that's the idea behind the definition. That number, that limit L, is actually the value of the horizontal asymptote. You might have seen these in your previous courses, horizontal asymptotes. But if that limit exists, it is a horizontal asymptote, y equals L, if that limit exists. The graph can only have 2 of those at most. And actually, all graphs don't have them, but some have 1, some even have 2. Okay, now we're going to use this idea here. We have a function that's in this form, c over x to the r. C is any real number, and r is a rational number, positive. This limit will automatically be 0. We're not going to prove that, but we're going to take it as fact. Okay, and of course the opposite, when x is heading to negative infinity, we have this situation. It's still going to be 0, that limit. Okay, now we can use that to help us with lots of these different forms of limits. Here's our first example. Okay, so the first part here, we do a direct substitution. Let x run to infinity. We notice we have the exact form that we had before here. Can't see my signs there. So we have the same form here. This is going to head to 3. This portion is going to head to 0. So our answer will be 3. Okay. Now the next one, this one, I have a little bit of an issue here because this is not, it's not this form 1 over x to the r. So what we can do is try to do a little bit of a division here. So what we're seeing is this numerator is heading to infinity, and so is the denominator. So what we'll do is this. We'll take and divide by x, divide that denominator by an x. That gives us this. And what's good about this is that now we can handle these forms. This is going to 3, this goes to 1, and this goes to 0 based on our special limit theorem from above. So what we have here is a 3 over 1, or just a 3. So that's how we can handle it, that type of problem. Here's another one. We'll treat this the same way. Notice that the numerator heads to infinity, so does the denominator, but we can do a little bit of algebra. And this time you're going to divide by x squared. Okay, and that becomes this. So what we're seeing is a 3 up here, and both of these are zeros down here. These fractions become 0. So this is a 3. Whoops. 3 up here, 0 down here. This is undefined. Okay. Undefined because we have 3 over 0, so this does not exist. Let's say DNE. Okay. Now, to that next one in the next video.